Okay, let's look at section 6.2, characteristics of the equation of polynomial functions. So the first thing I need you to do is to flip to page 392 of your textbook, like we did with last session. This takes forever. And, oh, here we go. All right, so page 392 of your text. So key ideas and the need to know need to go in your learning journal. Again, it's a lot of work. I know you could just photocopy the page if you wanted to, but I think writing it retains it to your memory. So when a polynomial function is in standard form, there's a few points that you need to know about that. So the maximum number of x-intercepts the graph may have is equal to the degree of the function. So for example, if you have x squared plus 2, your graph should have 2 intercepts, x-intercepts possible, right? Okay. The maximum number of turning points a graph may have is equal to 1 less than the degree of the function. Okay. So if you have x raised to the power of 3, it could have 2 turning points. Because that's just 3 minus 1 is equal to 2. That's a maximum number. It doesn't mean it's always going to have that number. The degree and leading coefficient, is the number in front of the highest degree order. So if it's 2x squared plus 5, your leading coefficient will be 2. So the degree and the leading coefficient of the equation of the polynomial function indicate the end behavior of the graph of the function. Like I said in last video, this is positive or negative. It depends if the graph is up or down or increasing or decreasing. And the constant term in the equation of a polynomial function is the y-intercept of a graph. So if I look at 2x squared plus 5 again, this 5 becomes my y-intercept. And we talked about that as well when we did sinusoidal function. So it's the same thing. Okay, so the need to know part. So linear and cubic polynomial functions with positive leading coefficients have similar end behaviors. So linear and cubic are the same. Okay, so linear and cubic polynomial functions with negative leading coefficients also have the same end behavior. Okay, so if I look at this example, so the leading coefficient on both of these equations is negative. So if it's negative leading on a linear equation, your graph is decreasing. And if it's negative on a power of 3 degree or a cubic function, it starts decreasing, turns, increases, and then continues to decrease again. Okay, if I look at the positive, so if the leading coefficient in a linear function is positive, your graph is increasing. And if it's a positive coefficient on a cubic function, it increases, turns, decreases, turns, and continues to increase. A quadratic, you should know from last time, has a unique end behavior. If the leading coefficient is negative, the graph extends from quadrant 3 to 4. So you learned last year, if this is a negative number, your parabola is upside down. So you have a maximum, and it starts in 3, and it ends in 4. If it's a positive leading coefficient, you know that your parabola opens upward, so it'll start in 2 and end in 1, because you always want to go from left to right. Okay. So if we go back to page 384 in your textbook, you will see on the side that there's the standard form of each equation. So standard form is just the generic form, like you know from our sinusoidal functions, the A, B, C, D. Okay? So the standard form of a linear equation is just an ax plus b, where a can never equal 0, because if a equals 0, then it would just turn into a constant equation. It wouldn't be linear anymore. Okay? The standard form of a quadratic you learned last year, so the a squared plus, or ax squared plus bx plus c, where a cannot equal 0. If a equals 0, then it would turn into a linear function. And the same thing for a cubic. Okay, so cubic is f of x, or y is equals a x raised to the power of 3 plus bx squared plus cx plus d, where again a can't equal 0. So let's look at an example here. You don't have this in your textbook, but it's on the whiteboard here. So I have a standard form of an equation. I have negative 2x squared plus 2x plus 4. Okay, so this is obviously a quadratic function. Since your leading coefficient is a negative 2, we know it's going to open up, or pardon me, open downward. And it's going to start in quadrant 3, and it's going to go up, and it's going to end in quadrant 4. Okay. The degree of the function is to the highest power, so it's a degree of 2. Number of x-intercepts, what we talked about, should be 2 as well. Your y-intercept should be your last term in your equation. Your end behavior goes from left to right. So if you just write Q3 to Q4, that's fine. The domain is always an element of the real numbers. The range is an element to your maximum number, right? Okay. So maximum value, and number of turning points on a quadratic is 1. So let's check our answer with what the book had here. Okay, so they actually graphed it on a graphing calculator, which you can do, which we'll talk about in next section. Okay, so you have 2 degree function, 2 x-intercepts, 4 is y. So quadrant 3 to quadrant 4, x is an element of the reals. They actually graphed it. So you went, it's less than or equal to your maximum value. So that's what I should have put here, less than or equal to your max value. And y, or 1 for number of turning points. So let's do another one here. We have another x squared plus 6x, or minus 6x plus 12. Once again, this is a quadratic because it has a x squared. So this quadratic is going to open upward because it has a positive leading coefficient. And the degree of the function is 2. It's based on this number. Number of x-intercepts is also 2 because it's based on that. Your y-intercept is your 12. Your end behavior goes from quadrant 2 to quadrant 1. Your domain of any of these equations is always the same. It's x is an element of your reals. Since your parabola opens upward, this is going to be y is the minimum value. So y is going to be greater than or equal to your minimum value. And number of turning points on this graph will be a 1. Okay, let's see if we were right. Move this out of the way. Just move out of the way. Okay. So, degree of function 2, number of x-intercepts 0. You'd only know this if you actually graph this graph. Okay? So predicting's okay, but you can't actually know until you graph the graph. 2 to 1, x is element, minimum value, and 1 turning point. So let's look at example 1 on page 385. It says determine the following characteristics of each function using its equation. X-intercepts, y, end behavior, domain, range, number of possible turning points. So this is just like the one you did on number 3 and 6.1. So f of x is equal to 3x minus 5 is linear. So it should have only one x-intercept. It should have only one y-intercept. The end behavior, since 3 is positive, should go from quadrant 3 to quadrant 1 because it's positive. Your domain is x is an element of the reals. Your range is also y is an element of the reals. Number of possible turning points is 0 in a linear function. For the second one, you're looking at a quadratic, so you're looking because x is squared, that's your highest leading coefficient. So number of possible x-intercepts could be 2. Y-intercepts is 1. Your end behavior, since your leading coefficient is negative, it's upside down, so it'll start in quadrant 3, end in quadrant 4. Your domain is x is element of the reals. Range is based on your maximum number, so it has to be less than your maximum number. Oh, your y-intercept's 8, I should say. Forgot about that. And number of possible turning points is just 1. Cubic function for C, possible x-intercepts is 3. Your end behavior of this one, since this is positive, it's going to start positive, come up, so it's going to come from quadrant 3, do the little turning thing, and then go into quadrant 1. Domain is always element of the reals for x. Range is element of reals, and possible turning points can be up to 2. So if we look at example number 2 in your book on page 388, we're going to match the graph to the function. So before I would look at the equations, I would just say, well, I know this is linear, this is linear, this is a quadratic, this is a quadratic based on shape, and this is a cubic, and this is a cubic. Okay, so I look at A, or g of x. So g of x is negative x to the 3, so it has to be a cubic. So it either has to be the 4 or pardon me, let's just go 1, 2, 3, 4, 5, 6. So the 4 is the 6th graph. Since this is a negative leading coefficient on g of x, which graph should it be? It should be the one going down. So g of x should be the 6th function. So that's your g of x. Your h of x only has x to the 1st degree, so it's linear, so it'll either be 1 or 3. Since the leading coefficient is negative, it's a decreasing graph. Both of them are decreasing, can't use that. Then we'll look at negative 3. So negative 3 tells you where it crosses on the y-axis, right? So this one crosses at negative 3, and this one also crosses at negative 3. So that doesn't help either, okay? So we'd have to actually graph this to figure out which one belongs to which, okay? So j of x is x squared minus 2x plus or minus 2. So we're going to look for our quadratics, which is our 2 and 5, okay? X is positive, x squared is positive leading coefficient, so they're both opening up. Negative 2 is where it crosses at the y axis. So this one crosses at negative 2, this one crosses at positive 2. So this one has to be j of x. Okay, k of x is the other quad, so this one has to be k of x by elimination. P of x is up here, that one's g of x, and then our negative 2x minus 3. Okay, so if you look at these two graphs, you're going to notice more variation between how it differentiates from the y, or goes away from the y. So this technically should be h of x,
line 1.
and this then should be q of x. So if you want to compare them, so for the first or the two linear equations, we can always use our graphing calculator. So if I open my graphing calculator and I go into my y equals, I can easily type in both equations. So the first equation that I'm going to type in is the negative 1/2 x. So I'm going to use the negative button, and then if you want to put in brackets 1 over 1 divided by 2, if you know 1 divided by 2 is 0.5, you can also use that. So negative 1/2 x minus 3. And if I graph the second one, I can go, what is the second one here? Negative 2x, 2x. Let's see if my prediction was right. Negative 2x minus 3. And I hit enter. And it graphs. And I can go to my graph and look at it. My blue line, and I can't see my red line. Oh, there's my red line. Oh, it's actually the opposite of what I was thinking. Okay, So the blue line is with the negative, so the negative is actually farther away, negative 1/2 than the 2x. So if we go back to change our answer, this should be the q of x, and this should be the h of x. So if you learned anything from this, learn that the only and best way to figure something out with this is to actually graph it on the graphing calculator. Okay, so nothing's perfect. It's just a prediction when you're looking at a graph. So it depends what kind of wording you see on a question. So if it's saying predict behavior, or if it's saying determine behavior, you're predicting, you're just using the rules. If you're determining, you would definitely graph it. So the assignment for this section is page 393, number 1, 5, 6, 9, 10, and 14. Good luck.